Hello guys, this is Ajahn Saeed. I'm gonna be discussing the chapter 6 multiple integrals for you. So here you can see in particular double integrals and triple integrals. Double integrals for functions of two independent variables like f of xy, and triple integrals for functions of three independent variables. Okay. Starting with the double integral of a function of two independent variables like f of x and y. Sorry. So we know that when we have a function of two independent variables, it means f of x and y. The domain of this function is a subset of two-dimensional space. Okay. So you suppose that this function f of xy on a region in two-dimensional space, it means in xy plane, is defined and is continuous. So this region, in the domain of the function, could be of any shape. Like rectangular, non-rectangular, it doesn't matter. Let me show you this picture. You can see when we say the function f on R is defined and is continuous, this region R could be of any shape: triangular, rectangular, you can see heart shape, circle, of any shape, it doesn't matter. So let's see how we are going to define the integral or double integral of this function on a bounded region R. Okay, bounded region. So let me move on to this page. You can see we have a function like f of xy on a bounded region R is defined. R is of any shape like this. The way we are going to define the double integral of f of xy on R is very similar to the way we define single integrals. Look at here, this is our R, right? By some lines, okay, some straight lines parallel to x-axis and y-axis, we partition the region R. When we partition the region R, inside R you can see a finite number of a small rectangle. So inside each small rectangle, we choose any arbitrary point like xk, yk. Okay, and here you can see they said delta ak. So delta ak is actually the area of this small rectangle, which is the product of delta xk and delta yk. It means delta ak equals delta xk times delta yk. Sorry. Now look at here. You consider this sum. The sum of, okay, let's say Sn sigma k from 1 to n, f of xk yk delta ak. This sum, okay, this sum is called Riemann sum. Now, if we take limit of this Riemann sum when n approaches infinity, here they said delta ak approaches 0. This is equivalent to saying that n, it means the number of a small rectangle approaches infinity. We can prove that this limit exists, okay, and is defined to be the integral or the double integral of f on R, and it's denoted by this. You can see two single integrals on R, f of xk yk dA. Okay, this is how we define the double integral, just like a single integral. Okay, next let me explain about the geometrical interpretation or meaning of a double integral. Look at here. If function f on region R, okay, is positive. It means the values of function are positive on region R. So look at here. Let's look at this product here more closely. What does it mean f of xk, yk, delta ak? So look at here. Actually, f of xk, yk times delta ak is the area of each rectangular prism. Look at here, over each a small rectangle here on xy plane, we have a rectangular prism. Okay, so actually when you say f of xk, yk times delta ak is the area, the volume of each rectangular prism. So when you say sum of these things, these guys, it means you have the sum of the volumes of each of all these rectangular prisms. Okay, so with that being said, it means if you have a positive function on region R, when you take the double integral of f on region R, you can see dA equals dx dy or dy dx. This means volume. Okay, this is a geometrical meaning of a double integral of a positive function on region R. It means the volume, okay, here, yes, you can see. It means the volume of the solid bounded below by the region R and bounded above by the surface of the function. Okay. So remember, when we have a positive function on the region R, the double integral of f on region R means volume. Okay, volume of the solid, as you can see here in the picture.